one can actually quantitatively determine whether life exists elsewhere by going out in our own solar system and looking for places in our solar system which are habitable, where life can occur, and trying to find life there. And so while we expect that that life is going to be microbial or relatively simple, this is much more of a scientific inquiry than the search for extraterrestrial intelligence, where if you get a negative result, you don't really know whether these extraterrestrials are communicating or not communicating, or whether they exist or they don't exist. In the case of the search for life in our solar system, we are actually going to these environments and seeing whether life is present. So I'm going to talk about three environments in particular. The first one is Mars, which has been a favorite of science fiction writers as a potentially habitable place. The second is the outer solar system, the moons of Jupiter and Saturn, where thanks to planetary exploration, we actually know that there are environments that can support life. And then finally, I'll try to talk about the implications. Now, I'm a scientist, not a theologian, so the implications from the point of view of theology, I will be very interested in hearing your comments about. They'll certainly be a lot less authoritative than the science that I'm about to talk about, and so I apologize for that in advance. When one goes to look for life elsewhere in the solar system, one looks for places where the essential ingredients for life might be present, and that would be water, carbon, and sources of free energy. Now, it's possible there are forms of life that can exist in the absence of water, that perhaps can exist in other liquids like ammonia or liquid methane or something like that. But the chemistry of life that's understood based on looking at terrestrial life, and all terrestrial life, all life on Earth is biochemically essentially identical, relies on water. And so NASA's strategy, the US Space Agency strategy, has been to look for places where liquid water exists. Likewise with carbon, there's a lot of interest in silicon as a substitute for carbon. Nonetheless, carbon has, despite the fact that silicon and carbon occupy the same column in the periodic table, nonetheless, carbon is a much more versatile element in terms of bonding than silicon is. And at the temperatures where liquid water exists, carbon is what's called labile. It's able to move through a number of different phases, whereas silicon basically is a crystal or a rock. So water and carbon are essential. And NASA has constructed a very useful tool, which I show in this approximate graphical form, the NASA ladder of life, where we move from the lowest part of the ladder, which is determining whether an environment can support life, whether it's habitable, to increasingly more diagnostic tests for life, going from looking at materials in rocks that might be produced by life, for example, stromatolites, layers of fossilized bacterial mats, to metabolic products, to molecules that might have been formed in biology, to molecules that are actually key to biology that confer function and structure, such as proteins or lipids, lipid membranes, and then on to metabolism and growth and Darwinian evolution. So this column reflects this upward movement of increasingly diagnostic and increasingly more difficult tests for life, some of which can be done by spacecraft, exploring a particular planetary environment. Others may require bringing samples back to the Earth. And so we'll talk about both of those strategies as we move on to actually looking at potential sites for life. So let's talk first about Mars. Mars is our second closest planetary neighbor. Venus is closer, but has no liquid water, being closer to the sun. Whatever liquid water it contained early in its history has been lost because the solar irradiance is simply too high. and the water evaporated away and was called a greenhouse runaway. Mars, on the other hand, is farther from the Earth. It's colder. And the question has always been, is it so cold that life could not exist there or might never have existed there? Or in fact, is it a place where life does now or once existed? The environment of Mars today, at least the atmosphere and surface, is not conducive to life. The air pressure on Mars is on the order of what's called in millibars, which is thousandths of a bar. A bar is the atmospheric pressure here on the Earth, 1 bar, 1 atmosphere. The Martian atmosphere is somewhere between 3 and 6 millibars. So basically hundreds of times lower in pressure than the surface pressure of the Earth. As a consequence of that, ultraviolet radiation bombards the surface, sterilizes that surface, forms highly oxidizing compounds, essentially leaches chlorine out of the rock, and that chlorine forms compounds that are the equivalent of very strong cleaning fluids. So the environment for organics at the Martian surface is extremely difficult. Nonetheless, the Viking landers in the 1970s looked for life in the near surface, didn't find anything. And the later explorations of Mars focused on the question of whether Mars in the past might have had a more clement environment. And there's ample evidence of that from orbital missions that show river channels, valley networks, and deposits of what are called carbonates and sulfates that are indicative of times when Mars had standing liquid water. That in turn motivated the exploration of the Martian surface and sending increasingly sophisticated rovers to places on Mars where that liquid water was thought to have existed. And so the currently operating rovers on the surface of Mars today are first from the United States, the Curiosity Mars Science Laboratory. This is a selfie that the rover took of itself. That's on the upper left. On the upper right, the Perseverance rover actually imaged from the little helicopter that it carried along with it. The helicopter is called Ingenuity. And then at the bottom, the Chinese National Space Agency scored really an extraordinary success with its first attempt, which was to land a smaller rover, but still a very impressive feat in a broad plane called Utopia Planitia. And so this is also a selfie of the Zhurong rover. In this case, rather than a selfie stick, the rover carried a little portable camera, dropped the camera on the surface, and then backed away for this portrait with its lander system. So I want to talk first about the components of the search for life on Mars, what one is actually looking for. And the strategy is to identify areas on the surface where liquid water was present for long periods of time. Orbiter data indicate that there are many such areas, and the two places where the Curiosity and Perseverance rover have gone are Gale Crater and Jezero Crater. We'll see both of these in a few minutes. And then look for evidence of organic molecules, because if life is present or was present, there should be carbon-bearing molecules in those sites. And then number 3, look for evidence of current biology. And there is actually some tantalizing evidence at Gale Crater. I'll describe that. And then finally, if you really want to look for either evidence of past life or the faint traces of life today, using instruments that are available in terrestrial laboratories and laboratories on the Earth provides the highest level of sensitivity. What one can send to the surface on these rovers is always limited in sophistication because of the size and the power limitations. So the first rovers to really score evidence for liquid water, standing liquid water on the surface on a local level were actually 2 precursor rovers that NASA sent in the early 2000s, Spirit and Opportunity. These were solar-powered rovers akin to the Zhurong rover that China now has on the surface. They were limited in their roving capability. This is not a selfie in the lower left. This is a mocked up image. But the kind of evidence that they found was chemical and mostly geochemical. So in the upper right, you see an image of gypsum, which is a mineral that forms in the presence of water, a vein of gypsum exposed on the surface at the Opportunity landing site. In the middle, you see what are called blueberries, which are actually little concretions that contain large amounts of hematite, as well as another mineral called jarosite. And these are minerals, particularly jarosite, being an iron sulfate, which would have formed as water standing in the locations billions of years before where these rovers are now, would have gradually evaporated away. And these minerals would have been deposited on the surface as the water evaporated into space. And then finally, there's physical evidence of running water, something called cross-bedding. Cross-bedding, as you see in the lower right here, consists of layers that have a particular form to them that indicates flow of water or sometimes flow of wind. And the particularly detailed kinds of images that were returned by Opportunity suggest that this cross-bedding is not from wind-deposited sediments, but actually water-deposited sediments. So billions of years ago, Mars had a different climate than the climate it has today. It would have had to have had a thicker atmosphere in order for this standing liquid water to be stable. The very thin carbon dioxide atmosphere today would have been a thicker atmosphere, probably still of carbon dioxide with maybe nitrogen and other gases. But key to this is that the liquid water would have been stable for long periods of time. And so one of the places that intrigues scientists in terms of sending a more sophisticated rover is this crater, Gale crater, which you see here. The crater is 150 kilometers in diameter. It has in the middle of it a very high, in fact, 5.5 kilometer high mountain, which is apparently made of sediments that gradually piled up over time as standing water in this crater evaporated away. Some of those deposits may be windblown, but mapping of this crater from orbit shows that within the crater, and this is now an image from an orbiting satellite around Mars, things like clays, sulfates, both of which are indicators that in this crater and on the slopes of Mount Sharp, water was present and that the sediments were actually deposited in the presence of water. So the rover that was sent, the Curiosity rover, is actually plutonium powered. So it operates night and day. It's much larger than the Opportunity and Spirit rovers. It has operated since 2012 and has a very sophisticated retinue of science instruments, as well as a variety of ways to analyze rocks. It can actually fire a laser from this top pedestal here called ChemCam, which vaporizes elements from the rock, and those can be analyzed with a spectrometer, what's called a Raman spectrometer, or it can dig and actually collect rocky soil and pebbles and put them into a device called SAM, Surface Analysis at Mars, which provides a very detailed analysis not only of the elements, but the minerals that are present, and can detect organics and can also sample gases. So here's the SAM instrument in the laboratory at Goddard, NASA Goddard. Here's an image of the portal through which the soil is actually dumped to go into the instrument on the top of the rover. So what Curiosity found in Gale Crater was ample evidence just from its cameras of outcrops of material, partly buried by Martian dust, indicating running water and standing water in the crater itself. So here's an outcrop which contains pebbles of a variety of sizes. On the left is the image from the Curiosity rover in Gale Crater on Mars. On the right-hand side is an equivalent area on Earth where there was once a stream as well. And so the types of pebbles, the way they're sorted, the way they're cemented together strongly indicates the presence of water. And indeed, analysis of the rock from these areas on Mars, this part of Mars, indicates, again, evaporites, minerals that would have been deposited in the presence of water, and organic molecules. There are remnant organic molecules present in this material. And those organics are stabilized by sulfur. So they are kind of the last bits of organics that were protected from this ultraviolet radiation that hammers the surface by being partly under the surface, Curiosity dug underneath the surface, but also by being combined with sulfur, fixed with sulfur essentially. There are lake deposits as well that you see here in Gale Crater. There's Mount Sharp in the background. The most intriguing evidence for life is, in fact, faint evidence for extant life, existing life in that region. And that is a measurement by the SAM instrument on the Curiosity rover of small amounts of methane, which is carbon and 4 hydrogens, which is very unstable in the Martian atmosphere today. It's destroyed very, very quickly, and seem to have a diurnal variation to it, more abundant in the nighttime on Mars and less abundant during the day. Now, on Earth, most of our methane comes actually from cows, as well as microbes. It's possible that the Martian methane is produced by microbes that are underneath the surface and perhaps benefiting in the deep crust from the presence of water or hydrogen that might still be there. It is also possible for methane to be produced when water and rock react with each other without the presence of life. That will also produce methane. It's possible to tell the difference between these two by measuring the ratio of what are called the isotopes of carbon in methane. There are 2 stable isotopes, one that has 12 neutrons, carbon 12, the other 6 neutrons, which is called carbon 12, and 6 protons. And the other has 7 neutrons and 6 protons, carbon 13. Biology tends to favor carbon 12. And so you would tend to have an enrichment of carbon 12 in the methane relative to the background carbon dioxide if the methane was produced by biology. If instead it was produced by geology, you would expect to have an isotopic abundance similar to that of the carbon dioxide. Unfortunately, this amount of methane is so small that one cannot make that measurement with the existing laboratory in the Curiosity rover. It would require sending a different kind of instrument or possibly sending air samples back to the Earth. So while methane is definitely there, we don't know whether it's produced actively by microbes or by water-rock interactions. Either way suggests that there is liquid water underneath this very dry, very desiccated surface of Mars. So the second sophisticated rover is actually part of an effort to bring samples back to the Earth by NASA and its international partner, the European Space Agency. So the second rover, called Perseverance, was sent to another crater called Jezero Crater, which has on its western end a river channel, which is today dried up. And at the end of that river channel, at the eastern end of that river channel on the western side of the crater, is a river delta. That delta is very old. We know it's old because it's been punctured by impacts. You see this crater here, for example, and another one up here. The fact that the delta has been punctured by craters tells us that it was deposited billions of years ago and has basically now just been sitting there. So again, this is evidence of an ancient hydrosphere. And what one would like to know is whether there is evidence of life in these ancient deposits. So here's a terrestrial delta feature, the end of the Mississippi. It looks different because it's being deposited in the ocean here. If you were to drain the ocean away, it would look a bit more like the delta deposit at the edge of Jezero crater. When Perseverance landed some kilometers away from the edge of the delta, it took this lovely picture of the tongue of the delta. In the background is the wall of Jezero crater itself. And over time, it has been working its way to the edge of the delta. That was accomplished in April of this year, about 14 months after landing. The helicopter has accompanied it. So this is an orbital image with part of the path of the rover shown here, the current position of the rover shown in the blue bubble, and the helicopter just a small distance, about a half a kilometer away from it. So here's the edge of the delta in April, and you can see material that can easily be sampled as the rover would drive up to it. This rover, rather than containing a sophisticated chemical laboratory in its belly, contains a system for collecting the soil and rock, putting that material in metal tubes, sealing those tubes, and dropping them off in a location where a subsequent lander can pick that material up with its own rover and send that material back to the Earth. This is called Mars Sample Return. It's the next step in looking for life and understanding the history of Mars. And those samples that will be returned sometime in the next decade will be from Jezero crater, from the Perseverance rover. And so the process of collecting that material has just started. That will make it much easier to detect signs of past or present life, because laboratory instruments on the Earth, as I said, are far more sensitive than what can be carried to Mars directly. Nonetheless, this is an extraordinarily ambitious project joint between the US and the European Space Agency. It involves sending two landers, one with a fetch rover to collect the tubes, the other with literally a rocket to put this stuff back into Mars orbit. And then a third spacecraft will capture the capsule containing those samples and bring that back to the Earth. So that will be exciting to see. So that's the status of looking for life on Mars. I want to now talk about the outer solar system. There are three locations in the outer solar system where we have strong evidence for liquid water: Jupiter's moon Europa and Saturn's moons Enceladus and Titan. I don't have time to talk about Titan, even though it's a very interesting object where not only is there liquid water under the surface, but there are seas of liquid methane on the surface, which might be places to look for very exotic forms of life, non-terrestrial life that maybe could exist in liquid methane. That's very speculative. But Europa and Enceladus, despite their great difference in size, are both ice-covered moons which have liquid water in their interiors. And so Jupiter's moon Europa, which is about the size of our own moon, is mostly rock, but is covered with a layer of water. We know that most of that layer is actually liquid. We know that from an experiment done by the Galileo spacecraft in the 1990s, which measured fluctuations in Jupiter's magnetic field caused as Europa moved in its orbit around Jupiter and the magnetic field passed through this moon. This is a little bit like looking for bits of metal with a metal detector on the beach. You look for the conductive material, and in this case, that conductive material, being relatively close to the surface, according to the Galileo data, must be not metal, but liquid water. Liquid water underneath an ice crust, which, as you see in this image here, has been broken apart and shifted around, and that's geologic evidence for liquid water. How much liquid water? Well, the answer is a lot. If you take the size of Europa itself and the volume of the inner part of Europa that must be made of rock based on measuring the mass and the radius of Europa, and then based upon the estimated thickness of the ice crust of Europa, the rest of that being liquid water, what you come up with is that the ocean of Europa has twice the volume of water in it as the Earth's ocean does. So here in the correct sizes are the Earth, Europa, and our moon, and the little bubbles of water represent the size of the Earth's ocean condensed into a sphere. And here you see the equivalent for Europa. This is twice the volume of water on the Earth. So that's a huge amount of water present underneath this ice crust. We don't know whether that ocean contains salts, or I should say organic molecules. We do know that it contains salts. Those salts are required to have the kind of electrical conductivity that Galileo was able to discover in the fluctuating magnetic field measurements. And some ground-based data taken by Samantha Trumbo and colleagues at Caltech, Samantha now works as a postdoc at Cornell, shows that there are concentrations of sodium chloride salts on the parts of Europa that are the most geologically youthful, the places that look like the crust is thinnest. So the ocean of Europa, this ocean underneath the ice crust, is in places periodically coming out onto the surface and depositing salts. And some additional evidence for that comes from observations by Hubble Space Telescope, showing that at the southern latitudes of Europa, there's an excess emission of oxygen, which might be water, liquid water, spraying into space from cracks in the ice crust itself. So it may be possible to directly sample ocean material on Europa's surface. And that is the goal of the Europa Clipper mission, which will be launched in 2 years to Europa. It contains a very sophisticated set of experiments. The spacecraft will orbit Jupiter and make about 40 flybys of Europa. This is the pedal chart of its orbits. And every time it does that, it will make a variety of measurements to look for these ocean deposits, determine their composition, and as well to make some measurements by infrared, that's eThemis, and radar, the REASON experiment, to map both the structure of the crust and how deep the ocean might be. This is preparatory to deciding whether Europa's ocean might be habitable. And the question really comes down to, are there carbon-bearing molecules in this ocean? We'd love to have, as in the movie 2010 Odyssey 2, a large sea monster break through the ice and show itself to the cameras of Europa Clipper. But more likely, what will be measured will be deposits of organic molecules in geologically active areas. And that would point us in a future mission to places to land on Europa and look for the signs of life. A little preview of Europa Clipper, which will not arrive till 2029, will happen this fall. There's a mission called Juno in polar orbit around Jupiter, containing somewhat the same instruments. It's not really designed to look at the moons, it's designed to look at Jupiter, but it will make one close flyby of Europa in September of this year. It made a distant flyby last October, you see this image. But the September flyby will give us a preview of what Europa Clipper will see with its instruments. And particularly if a plume is discovered of a spray of material going out into space from fractures on Europa, that would be something that we would want Europa Clipper to focus on. The other moon that contains an ocean under its surface is Saturn's moon Enceladus. People always say, Encela what? It doesn't have as lyrical a name as Europa. It is much more poorly known. It wasn't the subject of its own movie. But it was the subject of Cassini's investigations in the Saturn system. Enceladus is a very small moon, only 500 kilometers across, and yet, as the Cassini spacecraft discovered, from these fractures in the south polar region, material is pouring out in the form of vapor and ice grains, creating a large plume, a ring around Saturn, and at closer range, in the lower left as you see, this material is coming out in individual vents in the form of jets. So there is a warm place underneath the surface. The surface is only 70 degrees above absolute zero, very, very cold. But evidently there is material that is quite warm. In fact, as I'll show you in a minute, there's strong evidence that that material is liquid. So here's a close-up of those fractures seen as Cassini made a very close flyby of Enceladus, a very tortured, carved surface from which these jets are emitting. So Cassini found multiple lines of evidence for an ocean beneath the ice crust of Enceladus. Even though Enceladus is quite a bit smaller than Europa, it's somewhat the same composition. It's mostly rock with an outer layer of water. And that outer layer is at least partly liquid. We know that from several lines of evidence. I'll go in order from the lower right to the upper left. Cassini measured high temperatures in the fractures. Instead of being 75 degrees above absolute zero, the temperatures at the surface of the fractures exceed 200 Kelvin. And if you extrapolate down 10 or 20 kilometers, you get down actually to the melting point of water. So the interior is hot enough for liquid water. Cassini was able to sample large ice grains by flying directly through the plume. Those ice grains contain up to 2% salt by mass, and that is more salt than can be dissolved in ice. What it means is that those ice particles were originally liquid. The salt was dissolved in the liquid water, salty water, and then as it came out through those jets, flash froze and then was analyzed by Cassini. So evidence that the ice grains are actually droplets of salty liquid water. And then the upper two lines of evidence are a little bit technical, but in summary, what they tell us is that this liquid actually exists as a kind of a global layer between the ice on top and the rock that is beneath. And in particular, the imaging observations of a very large rocking motion of the crust of Enceladus tells us that that crust is decoupled from the rocky interior. And what is decoupling it then must be a liquid layer, a liquid water layer. Remarkably, we know the composition of that ocean by sampling the ice coming out of these jets. That sampling is done with a technique called mass spectrometry. Cassini carried 2 mass spectrometers. They ionize molecules and atoms. Those ions are then passed through an electric field or magnetic field, as you see on the left. And by adjusting the strength and frequency of that field, you can tune for different mass particles. And so a mass spectrometer detects the mass of molecules or atoms from which we can identify their nature. And Cassini really hit a home run with these mass spectrometers. Here's one example. One of the mass spectrometers that analyzes dust found a strong signal of silicon and oxygen, with the peaks being in a ratio of 1 silicon for every 2 oxygen. That is SiO2. In crystalline form, we call that quartz. But these are very tiny grains. These are grains a billionth of a meter in size that are not crystalline, but have a size distribution that suggests that they were dissolved in warm liquid water, and that warm liquid water then, as it came closer to the surface and cooled down, allowed this silicon to precipitate out. And so this is evidence for some sort of chemistry going on between the rock and the water, because how do you get pure silicon dioxide? You get it with this lovely chemical equation at the bottom here. Take a common mineral, phaolite, which is a kind of an olivine rock with iron and silicon, react it with water, and you get another common mineral, magnetite, plus silica, plus hydrogen. We see the silica and we see the water in the plume of Enceladus. We can't see the phaolite or the magnetite. They're stuck down at the bottom of the ocean. But the test of whether this is right or not comes in the form of the hydrogen. Do we see excess hydrogen? Do we see excess hydrogen in the plume of Enceladus? That turned out to be a difficult question because the water itself as it's collected by the spacecraft at high velocity, produces hydrogen by impact. And with Cassini's mass spectrometers, we wanted to see additional hydrogen coming from this reaction. So in the very last fly through of the plume, using a technique that minimized the confusion between the water and the what we call the native hydrogen, detected a large amount of native hydrogen in the region of the fractures. And that suggests that this reaction at the bottom is really happening. And that suggests that underneath the ice crust of Enceladus, there's an ocean, and that ocean is interacting with warm rock at the base of the ocean to produce these hydrothermal reactions. The energy source for that heating is probably tides from the planet Saturn itself. The other spectacular discovery is Cassini discovered with his mass spectrometers lots of organic molecules. Methane, which you see in the here, is 1% relative to water. But on the right-hand side, you see another mass spectrum with the masses identified here at the individual peaks. And the peaks that are labeled as HMOC are separated by 12 or 13 mass units, which is equivalent to carbon or carbon plus hydrogen. And that's indicative of large carbon-bearing molecules, large organic molecules, slamming into the mass spectrometer and having the carbon or a carbon hydrogen unit breaking off to be analyzed by the spacecraft. So the ocean of Enceladus contains salts. It has water rock reactions producing minerals like SiO2 and organic molecules. Those are the basic requirements for habitability. So is this ocean endowed with life? Well, Cassini couldn't tell us that, but by flying back to Enceladus with a more sophisticated set of instruments and flying through the plume again, it may be possible to detect the biomolecules, the molecules from which life is formed. So this would be not detecting the cells themselves, which will be few and far between in the plume, but rather detecting the waste products, the microbial poop, if you will, produced by the metabolism of these microbes. So this would be a relatively simple mission to do. The mass spectrometers that can be carried today, as opposed to what Cassini carried, which was the technology of the 1990s, have the ability to very precisely distinguish between ions that have the same formal number of protons and neutrons, but are separated in mass because of what's called the binding energy of the nucleus. So with these mass spectrometers, for example, we could separate carbon monoxide from nitrogen, both of which have the same total number of protons and neutrons, have a mass of 28, but the actual mass is slightly different because of this so-called nuclear binding energy. This is a very powerful technique that is agnostic with respect to what molecules might be there, and it's a way potentially to look for life. So a number of us have proposed this mission to NASA a few times and haven't gotten there yet, but we're hoping for success this time. I want to talk now about what happens if we discover microbial life. The discovery of evidence of life on Mars actually has a rather problematic set of implications. Problematic in the sense that Mars is so close to the Earth that material has been exchanged between Mars and the Earth over billions of years. So if life began, for example, on Mars, there would have been quite a lot of these microbes potentially delivered to the Earth. Somewhat less for the Earth to Mars because of higher gravity. But nonetheless, this exchange leads to the conundrum that if we find evidence for past life on Mars, or even present day life in the form of primitive microbes, did those have a separate origin of life from the Earth, or are they the result of cross-contamination between these two planets, between the Earth and Mars? That is a problem that would have to be addressed by analyzing the biochemistry of these microbes, but even that might be ambiguous. Europa and Enceladus, on the other hand, are so far from the Earth, and their oceans are covered with ice, that the likelihood that there's cross-contamination with the Earth is really very small. And so as a consequence, if life is discovered, even simple microbial life in the oceans of Europa or Enceladus, it leads to the possibility that there was a second or even third separate origin of life, independent from the origin of life on the Earth. And so that leads to the theological question: is the origin of life a special creation, something that results from the intervention of God, or is it a part of the natural physical and chemical evolution of the cosmos? People have strong views on this. My view is very close to the Thomistic view that was articulated at a recent conference by Father Dominic Legg, and this is based on my notes, so it's not quite a quote, but it's pretty close. God endows the cosmos with real causal powers. Those causal powers, from a Thomistic point of view, we can call secondary causes. They're physical processes. And God acts in our universe, in the evolution of that cosmos, through those secondary causes. Those secondary causes can include the development of biology from chemistry. And scientific inquiry is that enterprise which attempts to reveal or tease out the secondary causes within God's created reality. So the primary cause, the uncaused first cause, is God. But what we analyze and study in the evolution of the universe and natural physical processes are the secondary causes. And if microbial life is discovered in the oceans of Enceladus or Europa, that would argue for these secondary causes as being at the foundation of the origin of life as a natural process, without eliminating, though, the essential requirement of an uncaused first cause, namely God, the creator himself. So we can debate that, but we won't know until we go and try to find life. So what if we do find microbes? What if we find a variety of different kinds of life forms elsewhere in the solar system? Why should there be so many places which are potentially habitable, so many planets in the galaxy, and some perhaps with life, if we discover life elsewhere in the solar system? Well, here again, theologians have an answer, and St. Thomas in 1273 wrote that multiplicity and diversity were reflections of divine wisdom. In his Compendium Theologiae, he wrote that the multiplicity and distinction existing among things were devised by the divine intellect and established that divine goodness might be represented by created things in various ways. And all of this was so that a certain beauty might shine forth from the very order existing among diverse things, a beauty which would direct the mind to the divine wisdom. So having abundance of diversity as part of the cosmic order, diversity in planets, diversity in chemistry, diversity in biology, are things that actually direct the mind to the divine wisdom and to a greater appreciation for God. Now, the church hasn't always thought this way, and there are always differences of views. In the Counter-Reformation, as Christopher Graney pointed out, Giordano Bruno was burned at the stake for a number of things, a number of heresies, but one of which perhaps was his insistence that there were countless other suns on earth, and the presence of that innumerable number actually glorified God. So sounds like theologians can be on both sides of the issue with interesting consequences. I want to close by addressing not the question of the potential abundance of life itself, but a question that I'm often asked as an astronomer and a Catholic, which is, how is my appreciation for the cosmos different as a believer, as a believing Catholic? It's difficult to approach this answer in a sort of a objective way, but let me try to approach it with two movies of a solar eclipse. The first of these movies was taken by the Perseverance rover on Mars. And what you're about to see is the Martian moon Phobos crossing in front of the disk of our sun. Again, this is from the surface of Mars. And a Martian looking at this eclipse wouldn't directly see Phobos because the solar disk is too bright. You would need filters. But this isn't a very impressive show. If you like irregular potatoes passing in front of the surface of the sun, this might interest you. On the other hand, what we see from the Earth in terms of solar eclipses is quite different. And here's an example. Here's a movie, if it will start. There we go. Okay, so I hope you can all see this now. What makes this eclipse different is that number one, the moon is round, and number two, the apparent size of the moon's disk relative to the size of the sun is nearly identical. The two are nearly identical, so that you get this remarkable moment, 7 minutes of totality, where you can see prominences on the edge of the sun and the solar corona itself, and stars very close to the disk, which allow you to measure the bending of starlight by general relativity. Now, all of this is fortuitous. It is, in a way, a cosmic accident, but it's a remarkable kind of fortuitousness because, in fact, it's one that has not been present throughout the history of the Earth. In fact, because the moon tidally evolves in its orbit, early in its history, the Earth had a moon that was much closer to us. So eclipses were longer and the moon's disk blocked out the corona. It would darken the sun, certainly, but you wouldn't see that beautiful corona. And likewise, as the moon retreats in its orbit from the Earth, in about 600 million years, there will no longer be total solar eclipses. All solar eclipses will be annular. So would it be appropriate to be a rationalist and say that this is simply an accident, but a very fortuitous and happy one? Or is this something that is in part for the human benefit, for our development of astronomy and appreciation of the heavens? I don't think we can answer that question from a rationalist point of view. We have to answer it from the point of view of faith. Actually, you can say that it's both. You can say that it is both fortuitous, a coincidence, and the work of God, because to use the analogy of the play and the playwright, the actors in a play may see events happening as being fortuitous, but these events have been created in the mind of the playwright, outside of the temporal sequence that the actors or the characters in the play are experiencing. And so, these are the kinds of things that we observe, we enjoy as part of our existence as intelligent, self-aware beings on the earth, and that are part of the glory of the heavens. And indeed, for those of us who believe that that glory is the result of God's handiwork, we know that those heavens declare the glory of God, and the firmament shows forth the work of his hands. Thank you.
Thank you very much, Dr. Lunine. That was wonderful. Both the science and those closing reflections were very, very beautiful. So thank you so much for that. We've got a couple of questions. First, Father Mariusz has a first question about. So you mentioned, what Mars's climate used to be like, and perhaps maybe even changes on Europa. I mean, do we understand the process by which Mars lost its atmosphere, or is that still like an open question we're working on?
It's still an open question. There are a number of possibilities. The views have shifted over time. It used to be that it was thought that impacts from asteroids and wandering comets eroded the Martian atmosphere away. Now, the view is more that Mars's lack of a magnetic field has exposed that atmosphere to the solar wind, and over billions of years, the solar wind has been the primary means of eroding away the atmosphere, charging the particles and carrying them away in this plasma coming from the sun. Measurements made by another Mars orbiter suggest that that may be the primary process.
Okay. So I had a question about, so particularly about the moons you were describing, and so you're talking about how there's the ice cap and then these plumes of like seemingly equal underneath and then the plumes coming out. Does the ice, or is there pressure on the water that is causing these to flow out like jets, or is it simply there's no atmosphere, so as soon as it comes near the surface, it just kind of drifts away? Or are these actually being kind of like forced out by some pressure? And is that just the pressure of the gravity of the ice? Or I'm just curious how that mechanism works.
Yeah, so that's a great question. So in the case of Enceladus, where we know these jets exist, Cassini was able to measure the rate of emission of material as a function of Enceladus' position in its orbit. And the orbit is not circular, it's slightly eccentric. So it turns out that there's more stuff coming out when Enceladus is farthest from Saturn and less stuff coming out when it's closest. And so if you look at the stresses on this ice crust, when Enceladus is farther away, those stresses would be less and these fractures would relax somewhat and open up a bit. And so what that suggests is that you have a warm ocean, that ocean, because of crack pressure, has been pushed partway up through those cracks and then is boiling. And when those cracks relax and open to space, that boiling water exposed to vacuum basically just comes out in the form of vapor and ice particles. So it's not a geyser in the sense of a superheated steam jet that you would find at Yellowstone, for example. Unfortunately, the best analogy is sort of a little bit, it's not very attractive, but it's the way that the space station does urine dumps, where they open a valve and the urine that's stored in a bladder basically jets out into the vacuum of space.
So a question here from Father Mariusz. So you described again, and just adding a little bit to this, you mentioned sort of the kind of ladder of life at the beginning of what are the signs you would have, and that's particularly ordered, it seems to me, and I'm extending on Father Mariusz's question a little bit towards microbial life.
Yep.
Are there additional things, like what additional things would be needed for the possibility of more complex life? So more complex, multicellular structures. Is it just the same stuff, or are there additional features do we think we have any idea what they might be?
Right. So for complex multicellular life, or what's sometimes called metazoans, the best indicator would be actually imaging one of these things. And of course, you can't do that by flying through the plumes. So you would have to argue that, somehow you'd have to get down into the ocean and try to image these things. That would be hard and raises issues of contaminating the ocean with terrestrial biochemistry and so forth. The other possibility is if you are able to do a really good chemical assay of the material coming out of the ocean, either in the form of jets on Enceladus or on Europa landing there and sampling deposits. Metazoans on Earth, their cells have somewhat different chemistry, molecules like sterols, for example, that you don't actually see in microbial life. And so you could potentially look for complex biomolecules that we know on the Earth occur in the cells that make up complex organisms, eukaryotic cells. That doesn't directly tell you that they're large metazoans. It tells you that the cells are complex. They're like our eukaryotic cells with organelles. But it would be one step toward that at least. And then, in the case of Mars, where we're talking about rocks and sediments, digging up, sediment, bringing it back to Earth, and conceivably finding a microscopic but multicellular organism, that would be the clincher.
Okay. So one last question then from Caroline, and she asks about, I think in some ways, looking beyond the solar system too, and now with all the different kinds of evidence of exoplanets and the ability to recognize those sorts of things, when we do look out and see, the huge number of galaxies and the seeming plethora of these exoplanets. I mean, do you think, is there an argument for the fittingness in one direction or the other in terms of, would God have only created life here in this unique place, or would he have allowed it to, or is it more likely if he would have allowed it to exist throughout the universe? I'm just curious, maybe if you have your scientific / maybe more amateurish theological thoughts on the fittingness of that from the idea of God's creation.
Well, I guess I have to lean on real theologians, and probably really great ones. So I would lean on St. Thomas Aquinas and his views on, the multiplicity and diversity of things being a reflection of God's divine wisdom, and that, God isn't parsimonious, but is overflowing with the abundance of his creation as an expression of his divine will. I mean, that's as far as I think one can go. It does raise the issue of how one detects life on distant planets around other stars, where you can't go and sample, and where that life might be primitive, so they're not broadcasting TV shows to us. And that's really tricky. It requires looking for features in what are called the spectrum of the light from a planet, features that might indicate that life is there, like chlorophyll, for example. And the challenge in that has always been to be able to do that, even though these planets are lost in the glare of their parent stars. So there are a number of techniques. It's a sort of a separate talk to describe those techniques, but some of that will begin to be done actually by James Webb Space Telescope in the coming years.
All right. I think maybe so. There's just one last one that was kind of interesting. So you did mention, that for instance, the possibility that there could be non-carbon based life.
Yep.
Are there similar kinds of patterns we would expect for that life, like that we would be able to identify it, or is it sort of we'd have to know it when we saw it kind of thing?
So the answer to that is maybe. One of the things that we find with biology that's different from what's called abiotic chemistry that happens in the absence of life, is that abiotic chemistry tends to produce pretty much everything that can be produced in abundances that depend on how easy it is to produce that particular compound. So in a particular class of organic molecules, you often will get something that looks like a Poisson distribution. It rises to some peak and then falls gradually in some measure, like the number of carbon atoms. When you look at biological chemistry and you analyze what's in cells, it's nothing like that. Biology needs specific things and specific compounds. So you get these very strange peaks of particular compounds, abundances in compounds that are nothing like what you get in abiotic chemistry. And regardless of whether it's carbon or silicon or something else, that really is the signpost of life, that life is information rich and very specific in the compounds it makes. And so that's kind of what you'd look for, is something that doesn't appear to be a random chemical process.
All right. Well, thank you very much, Dr. Lunine, again for your wonderful talk and for taking the time to answer our questions. One sort of final announcement. So again, we have one more talk in our online science and religion series, which will be next month, June 7th. At the same time, Dr. Sophia Rameau will be speaking on neuroimaging and what it can tell us about human beings. So thank you very much. And thank you very much, Dr. Lunine, for